So welcome back once again and to a new chapter, Electromagnetic waves, where whatever we have done before, in addition to that, we'll talk about what is the displacement current, something which was kind of discovered, kind of proposed, kind of explained, okay, and kind of established by none other than another great man, a Scottish scientist, James Clerk Maxwell. Was born in Scotland 1831, but he died in 79. So, a young age of 48, by all means. And he was a theoretical physicist, thinking physicist, and he too was a thinking physicist. This is Heinrich Hertz, a German scientist who died younger, 11 years younger to James Clerk Maxwell. These are two greats of that era. They were contemporaries, and their contemporaries also worked a lot. So, Maxwell the Great, Hertz the Great, and before that, Faraday the Great. Okay. That's my assessment. Now let's see. What are the things after electrostatics which is defined by the Coulomb's law or the Gauss law for electricity? Integral E dot dA, where E is the electric field and dA is the area vector. This is equal to the charge contained in that closed surface divided by epsilon naught, and of course this equation we are writing for vacuum. Okay. So this is one of the mother equations of the electromagnetic systems. So let's go ahead. I talked to you about Ørsted's discovery of magnetic field when current is passing through a conductor, and explained by Bose Memorial, okay, the presence of magnetic field associated with a current carrying conductor. And if currents are flowing, then the two conductors, which are infinitely long, they attract each other, okay, and if the current directions are different, then they repel each other, etc. Of course, along with that, the application of vectors and Lorentz force F is equal to QE plus V cross B, QV cross B, etc. And then came the beautiful Ampere circuital law. Integral B dot dl, which is a line integral along a closed loop, this is equal to mu naught R. Okay, the current which is passing there. Right now when we are talking about, I can write this as the current which we call the conduction current. Okay, the conduction current. So I have this integral B dot dl is equal to mu naught I C, the conduction current. Doesn't matter, you can put it as R. Then came the day when Michael Faraday in England and Henry in the US, they established that EMF is equal to minus d phi b or dt, where phi b is equal to b dot a. Okay, this we call with the minus sign, which is put by Lenz, another German. Okay, so this is England, America and Germany combined. We got this. That means, what does that mean? That an EMF is generated if there is a change in the value of magnetic flux. When Maxwell was, he put a question and he answered also this question, that if this thing is happening, is the converse possible? Is the otherwise possible? That if there is a dE dt, I'm sorry, I should have written. If there is a dE dt, does it give rise to some kind of a magnetic field? Because there is a dB dt and that gives rise to an electric EMF. But if it is there, do we get a magnetic field? This question, first of all, I will explain to you, and then yes. The answer Maxwell gave was yes. And this yes is so important, so beautiful, so unifying, that Maxwell put forward some laws. I will come to them. Okay? But before that, let me talk to you about a capacitor, a parallel plate capacitor. And at certain instant of time, let this be positive and let this be negative. Okay? And they are connected by conductors. So, now look here. If suppose there is no current, and when there is no current, IC will be equal to 0 if Q is a constant. This is charged. No change in the charge. Okay. But IC is not equal to 0 if the charge is changing. Either the charge is increasing or the charge is decreasing. Presence of a charge over here gives rise to an electric field. Clear? Electric field. And if the charge changes, then the electric field also changes. If it increases, so the capacitor kind of reacts. The capacitor kind of reacts, and the reactance is 1 upon omega c. Okay. So, if omega is more, then the value of the reactance will become less. So that means higher frequency will pass readily through the capacitor, and lower frequencies, they will pass. Currents will be there, but that will be kind of impeded, reacted upon by the capacitor, etc. Okay. Now, suppose I talk about this wire and make a circular loop. Okay, here. Then this is what I've shown to you. The wire is coming out like this. Okay, if I hold it, with my right hand, with my thumb out stretched, you can see. Then the fingers, they go like this. And accordingly, the magnetic field direction I have decided, and this happens to be this particular case in the anti-clockwise direction. Okay. Now, so this is Ampere's law. Ampere's law, like this. This holds. Integral, line integral, B dot dl is equal to mu naught into IC, which is called the conduction current, and this is due to the real motion of charges. Of course, the current is taken as the flow of positive charges, and we understand that it's the flow of negative electrons which takes place over there. Okay, and the information is passed on at the speed of light, very fast. So we have what I have here, I have written over here, the contour integration, the line integral B dot dl. So following Maxwell, let us draw a, like before in the first frame, in figure A, I have this plus I draw it like this. So the bottom of these plates is in between these two plates. Okay. What happens? That the bottom surface within this, that does not conform to integral B dot dl mu naught IC. Does not hold. And similarly, in the third picture, what I have is this is also open and this one is also open, and from the plate, positive plate to the negative plate, I have elaborately shown that there are lines of field, electric lines of field which are passing, which are uniform and parallel to each other. Okay. Now the question was, in this case, whereas you can find this P and you can get this IC here and IC here, and that current is there, but if we try to find this thing, then because there is no IC, between the plates there is no flow of charges at all, like is the definition of a conduction current, which is flowing here and flowing out of it. Okay, so inside there is nothing. But, and that means that there is a contradiction which is happening. So Maxwell said, he questioned, is there anything which is passing this surface S, okay, which is perpendicular to the lines of field which are passing from positive to negative, and just like this surface, also a surface which is perpendicular to the vector E. Okay, the answer is yes. Through this ring or through this challa, which is vertical, okay, parallel to the plate, so that the electric lines of field are going like this, there is an electric field which is passing through it from one surface to the other surface, the surface area being equal to A. Okay, so if so, we can say that electromagnetic electric field is equal to Q upon epsilon naught divided by A. Okay, and that the vector E is perpendicular to vector S. So I can write the flux, electric flux, which is passing through this as equal to the electric field dot dA integral, and therefore it is equal to E into A, and therefore I can write this Q upon epsilon naught A into A and A cancel out, and we get Q upon epsilon naught. Okay. So if I now differentiate it with time, d phi E or dt is equal to 1 upon epsilon naught dq dt, and this gives us dq dt is the current, so epsilon naught multiplies here, and I can write that I is equal to epsilon naught d phi E over dt. So this has got dimensions of current also. Now this current, which is passing by the way of what we call displacement, that is occurring over there, this is named as ID. Okay, this current is called the displacement current. So the total current of the system is I is equal to IC plus ID. Okay, of course IC plus epsilon naught d phi dt etc. So that means when we are applying the Ampere Maxwell circuital law here outside, then the ID is equal to 0. But if we are applying it inside anywhere, then ID is not equal to 0, but instead IC is equal to 0. Okay. So the total current becomes equal to IC plus epsilon naught d phi e over dt. So therefore we can write that integral b dot dl is equal to mu naught IC plus mu naught epsilon naught d phi e dt. Okay. So what it, and then I had given you the 4 Maxwell's equations. So they hold. Okay. This is Maxwell Ampere law or Ampere Maxwell law. So this was the beauty which connected the electric field and the magnetic field. It means that if there is a time changing electric field, there will be a magnetic field. And if there is a time changing magnetic field, then there will be an electric field. So this kind of a connection, that actually is the reason why we have electromagnetic waves. So Maxwell connected everything and found that if we have LC oscillations, then electromagnetic waves are propagated, and therefore he could combine electricity, magnetism and optics. And he found that the great controversy actually for light, Newton proposed that light is very fine corpuscles, okay, which are moving in a straight line. His contemporary Huygens said no, they are just like waves, like the waves on the surface of the water, like the waves which are responsible for sound propagation. So they are waves. But Newton said no, no and no. And finally he gave an argument which was very interesting. Light, sound, that if you are speaking to someone and there is an opening and your speech will travel like this, and a person who is standing somewhere over here will listen to what you have said. That means that the energy bends round the corner to go to the ear of this person, and this is called diffraction. Okay? Newton, he said, and he argued that if light were waves, they should bend round the corners. And he studied the phenomenon of propagation of sound very thoroughly, but forgot. It slips, and it slipped Newton's mind that the phenomenon is observed only when the opening or the obstacle is of the size of the wavelength. And the wavelength of light is very, 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 very small. Diffraction could happen, it will happen later on. But his argument was that the velocity of light in water, for example, would be more than that in air. The counter argument was that it will be less than in the speed in air. And it so happened, with the help of Young's experiment, that it was proved that the velocity of light or the speed of light in water indeed is less than that in the air. Anyway, but Newton was, he was taken as great at that time. But once Mr. Maxwell came and he combined these things, then it was established that light is electromagnetic waves, and light and electromagnetic waves, they travel with the same speed c, almost 3 into 10 to the power of 8 meters per second, etc. And that was established by the other genius at that time, Heinrich Hertz. And of course, the electromagnetic waves can be generated, they can be detected, they can be propagated, etc. So, for a very short period of time, not more than 30 years, it was later established that yes, the waves are corpuscles, and then another 20 odd years to say that yes, the corpuscles are also waves. So dual nature of wave corpuscular theory, that was established for light, etc. Okay. It was a pleasure to introduce this equation to you, Maxwell's equation. The great man Maxwell, he found that the equation, this part does not suffice inside a capacitor. Instead he gave his idea of displacement current. So let us give him a big salute, and to Heinrich Hertz, who died very young age of 37, a remarkable physicist, experimental physicist. Let's again say salute to him also. Thank you very much.